The scientific revolution starts now.
Deepest Descent podcast.
Let us see in the dark.
My life's work began when I was a 17-year-old in 1957, taking introductory psychology as a freshman at Dartmouth College. And that year, I introduced the field of neural networks when I was inspired by psychological data about how humans learn. And I was led to mind and brain because brain evolution needs to achieve behavioral success. So without brain mechanisms, you can't explain psychological functions, including learning. And without going into the details of what my work was about, I published the book I just showed you, my magnum opus, which is aimed to be a self-contained and non-technical overview and synthesis of not only many of my own discoveries over the intervening 60 some odd years, but also tries to explain data of hundreds of psychologists and neuroscientists and gives comparative analyses with their own theories. So in the book and in my work, one begins with perception, both visual and auditory, and then moves up the ladder to cognition and emotion and action. And in both healthy individuals and people who suffer from clinical disorders, including Alzheimer's disease, autism, amnesia, post-traumatic stress disorder, attention deficit hyperactivity disorder, etc. And you might say, well, how did I come to have anything to say about clinical disorders? As with a lot of my work, I never intended to do so. We could come back to that later. But more than that, my work describes perception, cognition, emotion, action cycles, whereby our brains interact ceaselessly with the changing environments to which we're exposed and how we learn to adapt to them. And as I indicated, all my work is about how brain evolution achieves behavioral success. And that just says that Darwinian selection operates over evolution to select designs that have worked. And I've explained, and it's summarized in my book, how multiple brain circuits and multiple brain regions interact to generate the properties that control the observable behaviors that constitute our daily lives. So mind is an emergent property of these brain interactions. And in order to understand emergent properties of brain interactions that represent mental functions, a purely experimental approach isn't enough, nor are traditional concepts from computer science or engineering or artificial intelligence. And so I, and then later many gifted students and postdocs working with me, introduced biological neural networks that could do so. And, for people who wonder who I am, since those early beginnings where I introduced the foundational equations and some of the core models in 1957 that are still used today, I've been considered the leading pioneer and leading current theorist of how our brains make our minds. In fact, if you look at the history of this, already by 1989, I had gone from MIT to get an endowed chair at Boston University. In 1989, I was invited by the university to give what's called the annual university lecture, and the president of Boston University at the time, who's John Silber, who was a notoriously tough guy, talked to a lot of people before he introduced me to a general Boston audience, and he called me in 1989 the Newton and the Einstein of the mind. So that just sort of gives you a data marker of, at least in our field, how at least some people think of me. And along the way, I needed to introduce new computational paradigms to explain how our brains make our minds. So it isn't just, little incremental stuff. We're talking about revolutionary leaps. And one of them is called complementary computing, which explains the nature of brain specialization. I mentioned complementarity in the brain before in commenting about complementarity in physics. And a second paradigm is called laminar computing, because it turns out that all higher forms of our biological intelligence, our perception, our cognition, our planning, our action, are generated by variations of a single canonical laminar cortical circuit. Our cells are organized often in 6 characteristic layers and sublamina. And that includes our vision, our speech, our language, our cognition, and so on. So it always seemed remarkable to me that such seemingly different behavioral competences all emerge out of variations of a shared canonical cortical circuit. And because of that sharing, which we can't take for granted, that's what, among other things, enables all our modalities to interact together in moments of unified conscious experience and enable us to accumulate the lifelong experiences that become a self. Now, essentially all my deepest discoveries came from insights about how our brains self-organize during both childhood development and adult learning. And it was a big surprise to me when our models of learning led to insights about consciousness. In fact, I think it's sad.
Why did that surprise you?
Well, first, I never tried to understand consciousness. You don't wake up in the morning and say, hey, let's understand consciousness, one of the hardest, most elusive problems in science. And if you don't study learning the right way, it will not lead to insights about consciousness. For example, in AI today, everyone is very excited about an old algorithm. It's called deep learning today, but it just uses what's called the backpropagation learning algorithm, which was discovered many years before. In fact, Paul Werbos had already introduced modern backpropagation and did critical examples showing how it worked in 1974. You can't understand consciousness with backpropagation or deep learning because, among other reasons, it is a feed-forward adaptive filter. And in order to understand consciousness, as I'll indicate, if you let me describe it a little bit more, you need top-down learned expectations to generate resonant states in our brains. And already by 1980, I had predicted that all conscious states are resonant states, so that without resonance, I would claim you can't understand any kind of consciousness. And as of this point, I've classified with my colleagues 6 functionally different kinds of conscious states, explain a huge amount of data with each of them, and each of them occurs in different parts of our brain and has different functions in the regulation of behavior. Moreover, it's not true that all resonant states are conscious states, and I've given examples of that too with our models. So, but to get to that point, I had to first develop the most advanced cognitive and neural theory about how our brains learn to pay attention, recognize, and predict objects and events in our changing, unique experiences in life. And I'm proud and grateful to be able to say that all the foundational hypotheses from which adaptive resonance theory, also called ART for short, can be derived, have been supported by subsequent psychological and neurobiological experiments, and ART's gone on to provide principled and unifying explanations of scores.
Hey guys, pardon the interruption. We need to remind you that we are entirely listener supported. That means we have no sponsors, no advertisements, nothing. Nobody telling us what to do, nobody cultivating our calendar. It's entirely coming from our patron base at patreon.com/demystifysci. Our patrons are everything to us, and we meet with them once a week through Zoom every Sunday. We get together, we figure out where this project should go next, and we really need your help there to sustain this and to make it something that's more effective. We want to be able to do these interviews in person. We want to grow this project. Now, if you don't have any money right now, that's totally fine. If you enjoy the podcast, just share it with somebody, leave a comment, engage with us, come over to Discord, tell us your thoughts. All of that is super helpful. But do consider patreon.com/demystifysci.
Of additional experiments. And so you might say, well, why has it worked so well? And that is an important question. And it gets to why I've been called the Einstein of the mind. And in 1980, in a very oft-cited paper of mine that I published in Psychological Review, which then, and I believe still today, is the leading theory journal in psychology, I was able to derive adaptive resonance theory from a thought experiment. And Einstein, you know, was very famous for the thought experiments that he used to derive special and general relativity theory. But my thought experiment asked about how any learning system can autonomously, all by itself, correct predictive errors in a changing world. So the very general issue. And the hypotheses I used to derive art in that thought experiment are familiar facts to everyone. They're things we all know because they're ubiquitous environmental pressures on the evolution of our brains over the millennia. And the reason we don't notice that is because often you don't take a few of these facts together and subject them to the kind of logical analysis of their implications when they act together to see how deeply they've influenced brain evolution. And also, none of these facts ever mention mind or brain. They're just environmental pressures on a self-organizing autonomous learning system. So that our principles and mechanisms, of which there are variations, and I'm not saying art is a complete theory, hardly any theory, if any, in science is ever complete. But because the hypotheses don't even mention mind and brain, art is a universal solution to the learning problem. Well, what is the learning problem? It was the question of how do you solve what I call the stability plasticity dilemma. Of because it asks how any system can learn quickly without forgetting just as quickly. So the plasticity is the learning quickly, and the stability is do not forget quickly. Another way of saying it, how any system can learn quickly without experiencing catastrophic forgetting. And if you've studied AI today, which is just the latest way to talk about neural networks, both backpropagation and deep learning do experience catastrophic forgetting. So they're unreliable, and that's because they are just feed-forward adaptive filters. But in art, you have top-down learned expectations. So what happens is an input pattern may come in. It's registered as a pattern of feature activations to different degrees depending on the importance of the features. Then that pattern goes bottom up in a one-to-many and many-to-one way to try to activate cells at the next level. These cells then compete with each other, and the ones that get the most evidence, that are the most activated, win, and those are the ones that can learn from the input patterns that they are selectively getting activated by. But if all you had was a bottom-up filter, then as in deep learning, you'd have catastrophic forgetting. But what happens is you activate a putative categories, and it immediately reads out a learned top-down expectation that tries to learn how to match with its adaptive weights what are the critical features that keep activating it. The critical features being the ones that are predictive. And the art matching rule, which controls how the form of this top-down expectation is defined by what's called a modulatory on-center, meaning it tries to modulate, excite, or sensitize the cells that it thinks are critical features, but doesn't fully activate them. And it inhibits everything out of the on-center, everything in the off-surround that is deemed to be an outlier. And it's only then if a bottom-up input pattern sufficiently matches part of that on-center that you get a kind of two excitatory against one inhibitory, and then you begin to fire. When you fire, you close a positive feedback loop, which coherently binds the critical feature pattern to the category and triggers learning through resonance, which is why it's called adaptive resonance. And
so let me see if I understand this correctly. So what you're saying is that there is a hierarchical system of, let's say, cells in this case, right? Neurons, and the neurons.
Let's call it heterarchical, because in addition to the hierarchical interactions, there are also horizontal interactions.
And so, what is the word?
Heterarchical. Often people mean if you have all sorts of interactions going on in a hierarchy, but it's not strictly hierarchical. I just want to emphasize.
It's cross-networked as well.
Yeah, so it's lateral as well as vertical.
And it can be multimodal all at once. You know, you could have data fusion between vision and audition. So.
Mm-hmm. But basically, you have a system into which you can get some kind of input that comes from a sensory module. From the world. So yes. there's the world, there's a sensory module. The sensory module feeds into this heterarchical system. And the heterarchical system has a pattern of characteristic excitation and inhibition that occurs at multiple levels. And that entire system, when it hits you're saying that it hits a resonance state where the topmost level is feeding back down into the lowermost level, and the lowermost level is at the same time feeding back up into it. And so
let me comment on that, because at first there is nothing trained above the level below.
Mm-hmm.
So as you start initiated response at the category level, then it, as you say, can start iterating that process, okay? And eventually you can get learning throughout the hierarchy. But I don't think there's evidence to say that it all happens all at once. For example, we know that in experiments on suturing one eye and how it influences visual adaptation, these are classical studies due to Hubel and Wiesel, among the reasons they got the Nobel Prize. It really only went to parts of the brain, retina, lateral geniculate, cortical area V1, the first sensory processing stage. In fact, for many, many years, many years ago, Pat Goldman Rakesh was a wonderful neuroscientist, and we were at a conference, I forget which one, and she showed a kind of cross-section, a schematic of a brain, and she had little stick figures to indicate, I forget, each figure was 10 or 100 neuroscientists and what they were studying. And they were basically all in V1 with a little scattering of V2 because no one could get a handle on what was going on higher up, because most of the things that were measurably changing were low level. That's totally different today. Now there are people studying every facet of brain with multiple kinds of methods and correlating it with behavior.
I'm really curious why these two-way feedback loops aren't being incorporated in the quest for artificial intelligence. Okay, are people trying to approximate that with the user feedback? Is that the hope that we can replace that bottom-up system somehow?
Well, let me say a little bit more, and then ask me the question again. Okay? Okay. Because I have to tell you a little more to put it into context where I can give you a more interesting and informative answer. So, as I was saying, deep learning, backpropagation, similar algorithms are just feed-forward filters. But I was desperately trying to understand what I call the stability plasticity dilemma, which meant how can we learn quickly without catastrophic forgetting? And let me point out that it was that analysis of learning that eventually led me and colleagues to develop rigorous neural models of how we consciously see, hear, feel, and know things about the world. So I can only infer, but for example, Rumelhart, Hinton, and Williams, who published backpropagation in 1982, got it directly from Paul Werbos, who they didn't mention. So from the start...
Scandalous.
Well, some people in a classical mode would call it plagiarism. Some people would want to say it's somewhat solipsistic. And so Jeff Hinton promoted backpropagation, and then I had already in 1988 published a very well-cited paper in the journal Neural Networks where I listed 17 fundamental and really incurable problems of backpropagation and showed that adaptive resonance theory, which I just mentioned, had overcome them before 1980. And no one, and this paper's been cited, I think, 2,000 times, so it's not unknown, and it's in my book, this stuff, and I've lectured on explainable AI in the main neural network conference and gone over all this in 2017. It's on the web, it's on Facebook. Anyone who is interested and who knows the field of neural networks might have looked at my keynote. Among other reasons, I founded the International Neural Network Society. I founded the major international conferences in neural networks today. I founded the journal Neural Networks, which spawned the other computational intelligence neural networks journals. So it's not like what I have to say is not being noticed. Anyway, so since
that leads us back to the question that Shilo asked, which was, how is it that the neural networks of today aren't being designed with this in mind if you've been publishing on it since the 80s and if this is such a well-known phenomenon?
Is it just impossible to achieve? Is it just too difficult?
No, it's being done. In fact, people have designed neuromorphic chips based on, in fact, Carver Mead, if you know anything about analog VLSI, was designing his silicon retina based on my vision models. No. There is a huge number of applications and very large scale applications, like a CAD system was used by the Boeing company to design the 777. There are hundreds of applications. Just look at my webpage, look at Gail Carpenter's webpage. It's well known. But
in terms of artificial intelligence?
Okay, wait a second. I've been called the father of artificial intelligence. And Jeff Hinton has been called the godfather of AI. Now, put it in the context of movies, perhaps, but I am known in AI. AI is just the latest buzzword to neural networks, and in particular, just like, the phrase right to life has been co-opted by people who don't want women to get abortions, even though right to life is a universal thing. The phrase AI has been co-opted by a clique that wants to promote deep learning. And they do it very successfully because there's software and you don't have to know much. It's not as formidable as the brain. But Gail Carpenter, among others, put user-friendly software on an open access web page before 2010 for people who want to use art. In fact, there's something called Default Art Map, which is a parameter-free version of ArtMap that you can use. And people use it, and they have been using it. And in fact, Donald Wunsch at the Missouri MST, I'm forgetting what it stands for, it's Missouri Science and Technology University, has been using it for a very large number of applications and has introduced a variety of specialized versions with different front ends and different this and that can be optimized to different classes of applications. So it's very broadly used, but it's just like people who have fixed conspiracy theories. In the worst case in our present politics, they don't want to read what the factual evidence is. And some of them are so far gone, even if you read it to them, they wouldn't believe it because it's fake news. So there are certain cliques that just don't want to do a comparative analysis. But As
do
I
you put
pointed,
do you put Jeff Hinton in that clique?
he's the head of it.
So how does that's an interesting rupture, because the purported goal of the clique that has taken over AI right now is to create an artificial general intelligence that is far beyond the capabilities of a human and to usher in this next new age of technological development. And so if you take them at their word...
No, let me make a comment.
Okay.
If you just read my book, now my book is self-contained and non-technical, it provides a blueprint for designing autonomous adaptive intelligence in algorithms, autonomous learning algorithms, and autonomous mobile robots. There's a blueprint. Now, to get the bells and whistles of the blueprint, you just have to go to my webpage, which is sites, that's SITES .bu.edu. I'm at BU Educational Institution /Steve G, STEVEG, where there are over 560 archival articles that give you rigorous equations, parametric simulations, qualitative and quantitative unified explanations of psychological and brain data, and many large-scale applications in image processing, pattern recognition, prediction, and so on. And anyone in neural networks who isn't just following the clique would know this, but it's enticing to think all we know is deep learning, and now we're going to make discoveries about how the mind works, where at the very same time, the Einstein of the mind has already created this blueprint. So you might think, as part of what they would want to say is, and of course we'll try to incorporate the work of well-established modelists like Steve Grossberg and his many gifted colleagues, but they never don't. They're solipsists. I wish it weren't true. Like Jeff said, back in 2017, he had an interview in Axios, and he said, I have lost faith in backpropagation. We don't need all the labeled data. We should just throw it away and start over. But by that point, I had already introduced a huge amount of models with really deep confidence that had been tested in multiple ways. So we didn't have to throw it all away. He showed he wasn't planning to try to learn from others in the literature. And I gave a keynote lecture on explainable AI at the International Joint Conference on Neural Networks, which is the biggest conference in the world of people who model neural networks, where I pointed all this out. That was in 2017. It might be the link I sent you a day or so ago.
Mm-hmm.
And, if you hear my lectures, like on my webpage, there are many keynote lectures on lots of topics. I try to make the simple ideas clear that go behind all these discoveries. But then you have to face the hard reality of doing the rigorous mathematical work, the equations, the parameters, the simulations, the parametric data fitting, the predictions, the applications. And we've been doing that for over 50 years. So it makes me sad. I would have preferred it being a more cooperative effort. But the problem is the foundational problems I listed for backprop and deep learning, 17 of them, I haven't seen anyone say, Steve, you're wrong. They're really not problems. You didn't understand. Let me explain. They haven't said that. They're ignoring the problems and then saying, oh, well, this is the best game in town, which it is not. We better start over again. And in the past, when Dave Rummelhart, who I knew very well, who started working with Hinton when he was a student, when Dave tried to improve things, he plagiarized my model of competitive learning, which is one of the components that goes into adaptive resonance theory. It was pure and simple plagiarism, and he was ordered to stand down. So that was his notion of going forward. He could have taken the work and built on it. The problem is, and this is, let me emphasize, I'm a cup half full person. I'm an optimist, an incurable optimist. Just ask my wife. That's why at age 83, I'm still making discoveries 66, 67 years later. But, here's my optimistic take. People do the best they can until they hit a brick wall. Hinton knows he's hit a brick wall. And that is the moment where you test character. When people respond by saying, oh, well, there was this alternative approach or approaches. I never appreciated them. But now that I more deeply understand the problem of my approach, I can say, oh, yeah, that's helpful. Let me do better. But you can't do that if you don't have the skills, the training to do it, if you've been too narrowly trained. So I founded a department called Cognitive and Neural Systems, which for many years was the most famous department teaching graduate students and advanced undergraduates both everything we could about biological neural networks and artificial neural networks. And we never restricted it to just our work. We taught backprop, we taught neocosmotron, we taught convolutional neural networks. That's what our students had to know when they went out into the world. Of course, who knows what job they could get. We wanted them to be able to be versatile enough to deal with the fact that, especially in science and technology, everything's changing all the time. We didn't want to train them in just one thing. But even when I visited San Diego, when Dave Rummelhart and Jay McClelland were in their heyday, and they even said when I first met them that their work was inspired by mine. So I thought, wonderful. I'm going to have wonderful collaboration. As a pioneer, I was lonesome. That's why I started a department, a society, a journal. I wanted to build a community so that future students wouldn't be so lonesome. But anyway, all they taught their students was backprop. That was the way. And if you don't know enough, you can't adapt. And if you can't adapt, you resist change. And you dig in and you become a cult or a clique. And you keep pushing your product until you can't get any money out of it anymore. So money, fame, as long as you can keep the grift going.
But you said that they're hitting a brick wall. What do you mean by that?
Well, I'm saying Jeff said he hit a brick wall. He said he doesn't think that's how the brain works. For example, all the learning in deep learning and backprop is supervised. You have someone giving you the answer. And so he was saying we need to be able to do unsupervised learning. Well, the third item in my 17-item list, so he said this in 2017, my 1988 famous review paper, the third item was that art could do unsupervised learning or supervised learning or an arbitrary combination of the both. So they just ignored it. Anyway, it made me very sad.
Is there a difficulty? Is there some kind of hardware difficulty to building a system that is artificial, that's capable of performing the art functionality? Because it seems like, since it's so architectural and the rules are so complex, governing the way that these... Pardon me?
It just gated steepest descent. It's the simplest learning law. It was used by Cahonen and so in his application of my ideas on self-organizing.
Okay, can you explain that a little bit for us?
Yes. So the learning laws are generally, let's say you have a cell. Now we have to think in terms of patterns because our brains are self-organizing pattern processes, because everything in the world achieves meaning through patterns. So when you look at my face or I look at your face, I don't understand it pixel by pixel. I understand the pattern of your face. And then I can analyze parts and wholes by focusing my attention, using my top-down attention or automatic shifts of attention to say, oh, what a pretty mouth you have. Oh, what beautiful blue eyes you have. But we're processing patterns. Now I've lost my train of thought. What was I talking about? I got so into pattern processing. Could you repeat your question?
You were saying that the rules that govern the organizational feedback are simple.
Descent. So gated steepest descent. I didn't want you to think that it was just one cell sending signal to one cell. Because, Donald Hebb, who was a great pioneer in 1949, he had his Hebbian learning hypothesis. That was wrong. And, if you wanted to ask why, we could discuss it. I've written about it many times. It was wrong because he wasn't thinking about patterns. Because if you're thinking about a pattern, let's say I'm trying in the simplest way with no pre-processing to take one cell, it'll send one-to-many connections to a whole image plane. And let's just be simple. Let's say on that image plane, I'll have your face, but just in black and white. Okay? Well, the adaptive weights in a pathway that goes to a white region, let's say that adaptive weight has to get big, because white means you're on a lot. An adaptive weight to a dark region means that weight has to get small, because it's dark. So whatever your learning law has to be, it has to be able to go up or down in its pathway to learn the spatial patterning of that picture. It could be a picture of your face. It could be an abstract representation in the temporal cortex of a whole set of part-whole categories. Do you see the point, though? You have to be able to have the same law based on the postsynaptic activity. Its adaptive weight should go up or down depending on what it's sampling. Is that okay?
I think so, yeah.
I mean, I'm just still trying to understand.
But I have to finish. I have to finish, and then please defer. So I use the word sampling. So the adaptive weight in that synapse can sit abutting the cells representing whatever and not learn from contiguity. It needs an active signal to activate learning. That active signal is called a sampling signal. So the learning law in its simplest form is called gated steepest descent, meaning learning will occur if there's an active signal, meaning the learning gate has opened, and steepest descent means the adaptive weight tracks whether it's supposed to be getting bigger or smaller. Gated steepest descent. So it's not complicated. It's the simplest law that you can use to turn on a cell to learn something. But because of that, there are immense consequences. Of course, I can have 100 billion cells sampling the same network, and none of them will see what's happening there unless their sampling signal turns on. And so if you have a choreography of cells turning on at the right times, you can sample an arbitrary sequence of spatial patterns. You can sample an arbitrary space-time pattern, in other words. And you can do it with one cell. And that illustrates why very small grains can do very complicated things, right down to beetles and crustacea. Now I finished the thread, so hit me. I'll do my best.
Well, I'm just still trying to understand why this architecture isn't being implemented in things like ChatGPT. Can you help me understand?
First, it has been, parts of it have been put in chips, but chips aren't necessarily the best way to go. At MIT Lincoln Lab, I think in the 90s already, was putting it, I'm blocking on the phrase, this uber fast way of computing. You could compute art models in real time in the 90s. It's not too complicated. It's well known. And you don't need a room full of computers to do it, okay? Which you often do for deep learning, part of the reason being that deep learning can only learn slowly, which means the adaptive weights can just change a little bit on every learning trial. So to learn one thing, like one cat's face, you might have to present it thousands of times. Art can do fast learning. The adaptive weight can go to its new equilibrium in one trial without catastrophic forgetting. If you have deep learning or backprop to fast learning, the whole thing collapses. And Gail Carpenter showed art learning complete databases. In 1987 and 88, we had a couple of papers that demonstrating art doing that with fast learning in one or two learning trials, period. So
why isn't everybody all over it? That's what I don't understand. So what's wrong with the actual computer chips that prevent this from being implemented?
Oh, well, doing stuff in analog VLSI is hard. And some of the world's greatest chip designers were designing our chips. But it's not clear that that's the most cost-effective way to compute neural networks, because without the amount of overhead that goes into printing an advanced chip, the die could cost $1 million a pop. Let alone,
so it's like they're working with the existing infrastructure. They're using the chips that they've been using for these other processes.
No, you don't need the chips. All you need, I forget what you call it. All you need are these very fast systems that were already available decades ago that can run these systems in real time, and they have been run in real time.
But they're fundamentally different from the chips that are in use today?
Yes, just like a von Neumann computer is decomposing a representation into, on and off gates. It's a serial binary device, whereas brain is analog and parallel. So if you're going to simulate anything like a biological system, which is almost always analog and parallel, on a computer, you have to first decompose it and then recompose it. And then it depends on how fast the chips you got. And that's all fine. But the idea that you want to necessarily make biological chips for image processing, pattern recognition, cognition, whatever. I think if Google wanted to make an autonomous adaptive mobile robot with onboard chips, they'd have the resources to do it. And one of the great things about it, remember I talked before about laminar computing, which means if you had a chip die that made the canonical laminar cortical unit, then by specializing it in the proper network connectivity, it could do vision, speech, language, cognition, action. So you could do it, but it will require deep pockets. And the problem with our way of doing things, for example, one thing that happened with people who wanted and were designing some chips based on our stuff, and we knew all the greatest chip designers, don't get me wrong. You know, they're on a grant from DARPA. Of course, you know what DARPA is, Defense Advanced Research Projects Agency. Of course, DARPA was one of the few places that had deep enough pockets. And then, because the director of DARPA is a political appointment, and every president gets rid of the old director, suddenly the money would die out. And they weren't finished. That's just, you know, one of the tragedies of how America has done a lot of research. People have been doing their best to change it, and that's why in Europe, the Blue Brain Project, you know, my friend Henry Markram was given, I forget, was it 2 billion, 2 trillion, I forget, it was a huge number of money by the EU to do whatever he wanted to build a blue brain. We don't have that kind of, I mean, Obama tried to respond. I forget what his project was called. But that was aimed more at methods, as I recall, rather than models. You know?
It seems like somebody at Google would be very interested in this. And it seems like they have the pockets for it.
They do and they should. They hired Hinton. You know, but Hinton spends his whole life marketing. I spend my whole life creating. If you look at my webpage, I had a series of papers up to 2022. But what did I publish a paper on in 2022? You know, I'm an old man now. I've built foundations that can explain many things. So on my webpage in 2022, I published a paper on how humans learn and consciously can perform music with multiple different kinds of lyrics and melodies at variable rhythms and beats. So I was doing music. A few years before that, I had a paper on how painters achieve their painterly effects and how we consciously experience them. And I analyzed the aesthetic traditions of 14 different famous painters, including Matisse, Monet, Renoir, Rembrandt, and explained how we see their paintings and what choices they made among the brain processes that could have been used to make a painting to create their characteristic style. So I've been doing art, I've been doing music, I'm having fun.
Was Hinton the one that you said had plagiarized your model in the first place?
No, Rumelhart, Hinton, and Williams. I'm not sure if they were all involved. Rumelhart Rumelhart and not Hinton and Williams. Rumelhart and someone else published a paper called Competitive Learning that used the exact model, not only that I had published years before, but I forget what year it was. I was still a young man. There was a meeting called in Tempe, Arizona, and it was an NSF meeting because the people who organized it, Peter Kylene, David Hestenes, Robert Heck Nielsen, believed that I was the Einstein of the mind. Even then, they got NSF to fund a week-long meeting. What is it called? A CBMS or something? Some kind of meeting where all morning for 5 days there's a main speaker who talks, who tries to bring together discoveries of as many people as possible in the audience at the same time as they describe their own work. And Wilma Hart was there. And Heck Nielsen, I forget, I've lost track now, at some point emphasized, oh yes, Rummel Hart spoke offline, I believe, to Heck Nielsen that he would like to do competitive learning, although it's one of the things I discussed as part of my exposition of adaptive presence theory. And Heck Nielsen, in no uncertain terms, said, but Grossberg already did that to Rummel Hart. Rummel Hart knew. And for years before Robert Heck Nielsen died, he was a professor at UCSD as well as the founder of what was then called HNC software, Heck Nielsen Neurocomputer. And then it was absorbed into a bigger company and absorbed into. He taught his students at UCSD, where Rummel Hart was. If you want to understand neural networks, all you have to do is read Grossberg. And that's what he taught them. So this
it seems like the upsetting part was that he didn't develop your ideas at all. He just presented them.
There's a tradition of plagiarism and a tradition of, for example, in the case of backprop and deep learning, I did not do that. That's not what I do. It's non-biological. But let me give you some of the background. So I met Paul Werbos, who did bring it to its modern form. So before Paul, there was Shinichi Amari, who was a great neural network pioneer who did some work on it, and David Parker, who was at Stanford at the try to get backprop patented by Stanford, where he was working. They refused. They said there's no future in it. And then Paul Werbos, who I knew through my PhD student at MIT. I was then a professor at MIT. And Dan Levine, my student, knew Paul, who was then a PhD student at Harvard. And Dan told me that Paul was having a lot of trouble getting his thesis committee to accept his PhD thesis. And he said, would I be willing to meet with Paul? And I was happy to meet with him. And, it was a very long time ago, and Paul might have a different recollection. He's still very much alive. But my advice to Paul was work out specific examples to show how backprop worked. He had brought it into the modern version, and they should accept it. And they did. So Paul got his thesis in 1974. And although I don't work in backprop, I hope that I gave Paul good advice to help advance the field. And a lot of people realize that Paul deserved the real credit for it. So that was 1974. It was in 1982 that they were promoting it. I think that was Rummel Hart, Hinton, and Williams. And I was at a conference where Dave, who I knew very well, was talking, and he introduced it as if it was new. And I was sitting next to Gail Carpenter, and I said, but all this is known. And it apparently the people in the audience didn't know. And you might ask why. And I didn't get a chance to say it before. The fields we work in are very interdisciplinary, cutting across psychology, neuroscience, computer science, engineering, mathematics. And if you want to plagiarize by marketing someone else's ideas, you just have to sell them to an audience who didn't know them. And Dave was speaking to an audience of experimental psychologists who didn't know the models. So they said, oh, wow, isn't this great? Just like John Hopfield, I had made the discoveries that then Hopfield promoted to engineers who didn't know it. So this has been going on for a long time. There are different silos in an interdisciplinary field. It's just like if you look at the complexity of our political landscapes, how you might say, well, how do people in some of the southern and Midwestern states believe these absurd conspiracy theories? That's because they were listening to Fox News and only Fox News. They wouldn't listen to MSNBC or CNN and so that's their reality. So if you're in your silo and you don't have the wherewithal or the time, a lot of people who watch Fox News are very hardworking. They might have 1, 2, 3 jobs. They're busy trying to get by, taking care of their families. They don't have time to reach out. And unfortunately, Fox News dominates, the airwaves in parts of the United States. Which reminds me, I forget, where are you two now today physically?
We're on the border of California and Oregon.
That's what I thought. I thought you were up there. I love it up there. It's very nice.
It is very nice.
How long have you lived there?
It's like a year and a half now. We were in Portland before that. We were in New York before that. We were in San Francisco before that. I was actually at UCSD. Shilo was in Ohio, and so we've moved around a lot.
So, in Ohio, would you mean Ohio State or which?
Yeah,
which
actually,
Ohio?
One of the first labs I worked in was at Ohio State, actually.
Who did you work with? I know several people.
I was working in leukemia at the time, so probably not.
I wouldn't. No, I wouldn't know them. No.
Yeah, it was a great lab. The PI's name was John Bird, and he's a stellar scientist for sure. He's a doctor also, so everything was patient oriented, which made it really meaningful at the time. Mm-hmm. And I actually the first lab I worked in was at Yale, and it was kind of a disaster compared to the one that I found at Ohio State. I mean, Ohio State just has so much funding, and they're really well integrated hospital system with the laboratory research, and yeah, it was a good place to start off.
Yeah, well, I did lecture there in their psychology/neuroscience department a number of times. And one of my colleagues at the time, who I liked very much, is Jim Todd, who is an expert in vision. I forget who some of my others are. I also loved lecturing at Indiana. I did lecture in Portland at international conferences. And at least when I was in Portland, I was sad to see a lot of homeless people sleeping on the streets. I don't know if that's still a problem there.
Yeah, I mean, that's not just that, but the whole town is pretty poorly managed. It essentially drove us away from it. It's funny where we were living. We like to say that 2 of the 4 sides of our property burned down while we were there, literally. And one was maybe a meth lab type situation. One was a homeless camp. So it was just, and it's one of those things where they're throwing money at it and nothing's happening. The money ends up in the bureaucrats' pockets, and it's just kind of sad. So I don't know. It just feels like we're just going to keep cruising down the coast until we end up in LA one day, like everybody else.
Well, I loved San Francisco when I was there. I was a graduate student at Stanford from 61 to 64. And as I said, I had made my first discoveries as a freshman in Dartmouth. And it turned out that multiple departments at Stanford offered me positions, I think in psychology and mathematics and one other. And I had an NSF scholarship, so I can go anywhere. And at that time, Stanford had what was called the Institute for blah, blah, blah in mathematics and psychology. It was run by Bill Estes, who was a great pioneer in the development of models to explain psychological data. But Bill had a very famous paper with B.F. Skinner, if you heard of Skinnerian psychology, in 1941, where they were talking about fear. And but Bill was trained as an experimentalist. And as you say, it depends on the breadth of your training. He didn't have any training in math, computers, anything, but he was a very gifted man, and he struggled to try to model some of his group data of psychological learning using a finite Markov chain, which is just another way of saying it's an urn model. You are an urn. You might have two urns. One urn has unlearned elements. The other urn has learned elements. And learning gets elements to go from the unlearned to the learned urn. And forgetting, you go from the learned to the unlearned. And by computing probabilities in different aspects of the experiment of the probability of learning and unlearning, you get a matrix, and then you'd iterate the matrix multiple times to try to predict what the outcome of the experiment is. So it was very useful, but it was at best a metaphor, and it really didn't have a biologically relevant learning mechanism. And it had no architecture. There's no brain there. Anyway, at that point, I had been working as well as I could since 57, and it was then 61. And so I went to Stanford full of hope. But it was just a leap too far for Bill or any of them to go from a finite Markov chain to a self-organizing nonlinear system of differential equations linking brain to mind. And so I made the most of it. I took 90 credits of advanced mathematics at Stanford because I deeply believe that to be an effective theorist, it's like being a great concert pianist. You have to already have all your scales, all your technique at your disposal so that you can make music. And I believed I had to have all this math in me. So no matter what idea I was led to through the data, I would have the conceptual and technical tools to embody it in models in a natural and powerful way. So I learned all that math, but then when it came to writing a thesis, I wanted to write a thesis in math proving theorems about how my networks learned. They weren't having any of it. And the reason was, in part, that their specialty was fluid dynamics, which is a great classical field in applied mathematics. I think, people who do it well have changed our civilization, including the fluid dynamics of aerodynamics and airfoil theory, and how subsonic and supersonic airplanes, both commercial and military, fly. So it's not a criticism, but they just couldn't deal with this totally different paradigm, this new paradigm. So I was very sad. I did get a master's in math because of all my credits. So I thought, okay, I am going to go to a place where hopefully I won't be so much like a duck out of water. I'm going to go to MIT. And I wanted to go to MIT because Norbert Wiener was there. Do you know who Wiener was?
Mm-mm.
Well, Norbert Wiener was the founder of what's called cybernetics, which was really how to make machines smart like brains. And in fact, Wiener's work was one of the inspirations of John von Neumann when he introduced digital computers. He was stimulated by him and people like McCulloch and Pitts, who all had ideas about how to design machines that could learn and become smart. So my family lived in New York, and MIT is in Cambridge, Massachusetts. So I figured, okay, maybe when I'm in New York, I can visit what's called the Rockefeller Institute for Medical Research, now the Rockefeller University, because I was reading a lot of papers by great physiologists who work there. And I revered their work and I explained some of it. So I wrote a letter to Rockefeller asking if I could meet with one of those people. And what I got back, to my joy and surprise, was a letter inviting me, all expenses paid, to come to Rockefeller. So what was supposed to be just a way to see my parents in New York before going to see Wiener changed my life, because just as I was about to leave, Norbert Wiener died.
Mm.
So there went that dream, but I still had my trip to Rockefeller. And so I went to Rockefeller and they checked up on me, and apparently they heard good things. And so two events stand out in my mind. First, Rockefeller, do you know anything about it? There's no reason you should.
Yeah, we know where it is physically, and I think we had some friends that were studying there.
I'm telling you that it's a graduate university that focuses on cancer and medical research.
Well, that's part of what it does. That's what brought, there were a lot of Nobel laureates from Rockefeller who did great work. That's why it's called the Rockefeller Institute for Medical Research. But at that time, the trustees felt it was getting calcified. It needed new blood. But it needed new blood for many reasons, because to make these labs run, you need basically slave labor to do all the work. It was a feudal system. You'd have a lab chief who was the great man, and he'd tell, do this, do this, do that, do that. And if you didn't, you were out. And if you were out, you were thrown out in the trash. So at the time, they thought, let's recruit gifted PhD students to try to automate the process of feeding the laboratories. And I lucked out to write my letter just when they were recruiting. And so I'm flown in, and when you go to Rockefeller, it's right off, what is it, East End Avenue? I forget. It's between the easternmost avenue in Manhattan and the East River. And you go through this beautiful gate, which we came to call the Pearly Gates. And there was a little watchtower by the Pearly Gates. And wouldn't you know, the sweet man who was guarding it, his name was Angel. So we all saw an angel as we went through the Pearly Gates. And they put me up in a dorm. What was my dorm room? It was a furnished suite with a full bedroom and living room and a maid. And
wow,
that's incredible.
Out one window, I saw the 59th Street Bridge, which all lit up at night. And out of the opposite window, I saw the tennis courts. So I go into this heavenly place. I stayed overnight. The next morning, or at lunch, I met Mark Kotz. That's K-A-C. Mark was a very famous probability theorist who, basically just escaped the Holocaust from Poland and immigrated to the United States. And Mark was the senior mathematician in a math group that they were building. So it wasn't all medical. They wanted it to become more of a university, and it was the push to make it the Rockefeller University. So I met Mark, and the lunchroom continued the theme. Beautiful hardwood wall, beautiful inlaid walls, big windows overlooking all this beauty outside, linen on the table, silver, china, waiters and waitresses in uniforms, beautiful abstract $1 million paintings on the big walls. That's where I had lunch with Mark. And how did he test me? He didn't. We had an amiable chat whose most memorable remark to me was, "Steve, never grow old." Oh, well, that was an impossible dream. And Mark didn't live as long as he should have, but he didn't take good care of himself physically. He was a hedonist in the best sense of the word. And then after I saw Mark for lunch, just as the sun was beginning to set, I was ushered into the magnificent suite of the president of Rockefeller, whose name was Detlev Bronk. Detlev had been the head of the National Academy of Sciences. He'd been president of Johns Hopkins. And the name Bronk comes from the Bronx. It was his family that settled and governed the Bronx in New York hundreds of years before. So Detlev came from American nobility, American royalty, but he was a lovely man to me. I only know what I experienced. He ushered me into his exquisitely furnished office, and we sat side by side as the sun setting around us. And he looked at me very earnestly and said, "Steve, would you like to come to Rockefeller? All expenses paid. You can." Of course, I said yes, and that changed my life. And I then went to Rockefeller and I wrote my PhD thesis there. I had a wonderful mentor, Giancarlo Rota, who was a famous probability theorist, functional analyst, etc. But he didn't know anything about my work, but he also was an epistemological philosopher and was deeply interested in theory of knowledge. And here he had a kid who was trying to explain how our minds think. So he gave me protection. And as I mentioned, you needed protection because it was a feudal kingdom. And Giancarlo became my feudal protector. And at a critical point in my career, I had proved a whole series of global content addressable memory theorems. That is to say, I took my neural networks and I proved theorems about how they learn and remember for any initial state and how many times they even oscillate. These were very original theorems. But before Giancarlo could support me in my thesis defense, one of the wonderful things about him was his wild swings of happiness and generosity. But the dark side was he was manic depressive. So just at the critical point, he ended up in the Payne Whitney mental ward a couple of blocks away, which was very sad. I love that man. He taught us to enjoy Black Forest cake. He used to take us downtown. I'm blocking on his name, a really wonderful. Oh, the brasserie, of course. And he introduced us to Black Forest cake, all expenses paid, dinner, dessert. He loved to be generous. Anyway, so that left me without a feudal chief.
How far from graduation were you at that point?
Oh, I had written my thesis.
So you just had left to defend it, basically.
Well, you would have thought it would then become easy, but it turned out that the person was trying to fill his shoes. You see, Mark Kotz should have taken responsibility. But Mark was always away. Lecturing or, traveling here and there. I don't know exactly. He was on, national committees. He was doing useful work. So there was a vacuum there because it wasn't a full department. There were just a few faculty. I only went because I'd already gotten my course training at Stanford. So I went after 3 years at Stanford in 1964. So a fellow Mo Schreiber, who was struggling to make himself relevant at Rockefeller, and there were people who wanted to just dump him. He had no tenure. He was basically the galley slave of one of the other professors. I won't name names. Mo tried to become my advisor and take credit for my work, but I couldn't let him because Mo had interfered with my work before for reasons I can no longer remember. Ultimately, I got my degree, but it was a very strange committee. For example, there was no one doing what I did. Being a pioneer is hard, and we don't all survive. I survived through luck, intellectual power, and the fact I worked like a dog to be productive, more productive than anyone ever asked. And so my committee, including people like, I just saw his face and his name, Jürgen Mose. Jürgen was at the Quran Institute of Mathematical Sciences and a wonderfully cultivated man who was also one of the greatest theorists about, astrophysics and stuff like that. But he knew nothing about what I was doing. Why should he? It just was a foreign language to him. And the kinds of, he said, well, if, it should be that this is so, and it wasn't so. It should be that that's so, it wasn't so. He had no intuition into it. And that was the problem. But they realized that Mark, when he finally was forced to pay attention to it, Mark later, when he helped get a job as an assistant professor at MIT, said that I was the most original thinker he'd ever met. So he came through for me in the end. And that's how I got to MIT. And ironically, John Colorota, who was at Rockefeller, had gotten there just before I did from MIT. And he had been very unhappy at Rockefeller because there really wasn't much of a department there. And he went back to MIT and got an endowed professorship at MIT, where he was the only professor at MIT at that time who was a professor of mathematics and psychology. And he gave lectures about epistemology, I believe, in the philosophy department. So he was a wonderful and a very gifted, brilliant man. I really loved him. Very generous and kind. Anyway, so did I miss something there?
Do you think we could take a quick bathroom break, actually? I'm sorry, I have to use the bathroom. Would you mind?
No, I would love to. In fact, I'm amazed I haven't asked before you did. Okay. So, what do you think you want to talk about next?
Well, I really want to understand why people believe there is a hard problem of consciousness. We had Yosha Bach on the show last week, and it was...
I know Yosha, yeah.
Yeah, it was a very fiery conversation because we were fundamentally under the assumption that you and Ogi had really thoroughly addressed the problem. And we didn't understand why people still refused to accept that despite the fact that there is a mechanistic solution to consciousness, it is not accepted as an explanation, right? Despite the fact, like, at the end of the day, these people are saying, well, even if you have a mechanism, it's ultimately just a correlation. It's not actually a causative situation.
Well, if I can give a little framework for discussing that, and then we can continue going down whatever path you want. So to be complete, I should start by reminding or letting listeners know what is the hard problem of consciousness. And here I want to quote.
Yes, please.
So Wikipedia, so I'm going to read this. The hard problem of consciousness, quote, is the problem of explaining how and why we have qualia or phenomenal experiences. Then David Chalmers in 1995, who made the phrase hard problem popular, he said, quote, the really hard problem of consciousness is the problem of experience. When we think and perceive, there is a whir of information processing, but there's also a subjective aspect. Let me quote one more source. So we get a little consensus. The Internet Encyclopedia of Philosophy, quote, the hard problem of consciousness is the problem of explaining why any physical state is conscious rather than unconscious. It's the problem of explaining why conscious mental states light up and directly appear to the subject. And so we can meaningfully ask the question, why is it conscious? So let me make
these these statements to me are so perplexing because I look at it and I'm like, how could it be otherwise?
Well,
there's no other, for me, I'm a biologist, I'm a microbiologist. And from the microbiological perspective, I'm like, at the smallest level of the cell, there already has to be some rudimentary form of the system for being able to evaluate desired outcome versus current condition.
Okay, well, if you give me a little space, I can build up something leading to what I believe is an explanation of why we're conscious. The why question is what Josha may be stuck on. Not only that.
Well, what I'm really interested in, I understand your solution pretty well, but I don't understand why they don't understand your solution.
Well, I have to say more before I know what you think you understand. Okay? So, after I've said my piece, then I'm happy. So first, I think it's fair to ask, based on what I just quoted, what kind of event occurs in the brain that's anything more than a whir of information processing, and what happens when conscious mental states light up and directly appear to a subject. And it's here where I want to tie it with some of the things that I already said. So our brains sometimes go into a context-sensitive resonance state that can involve multiple brain regions. And as I noted, I've claimed that all conscious states are resonant states, but not all brain states are resonant. None of the spatial and motor representations in our brain use resonance. So consciousness isn't just a whir of information processing. So I think it's important for the audience to know what is a resonant brain state. So let me say that so we're not talking about who knows what. It's a dynamical state. Think of two or more levels, cells on each level with interactions bottom up and top down. It's a dynamical state during which neuronal firings across all the cells in this network are amplified and synchronized when they interact by reciprocal, excitatory, bottom-up and feedback top-down signals during a matching process. Remember, we talked about you can select the critical features to which you have learned to pay attention. So it's that resonant state. And so there are multiple kinds of conscious qualia. And I've done a lot of work on classifying them. And another thing to emphasize before stating what I believe they are is to emphasize that consciousness is there to help us adapt to the world. It's not just a platonic, I'm in the groove now. We see consciously to help us ensure effective looking and reaching. We hear consciously to help us ensure effective speaking and other communication acts like singing. And we feel consciously to help us be able to achieve valued goals. So it's all about how conscious states generate effective action. And I think I want to talk to you about one of the kinds of consciousness. Let me just prime myself a little so
I mean, what's really aggravating to me is that when you talk to these proponents of this being an intractable problem is that they'll say, we could design a robot that's capable of goal-oriented processes and would appear conscious, but it still wouldn't be.
No, it's not true. You wouldn't be probing it properly. So, let me give you one example of why I think we have to be conscious. And to do that, you're not just saying, "Oh, I want to explain consciousness today." So we'll talk about seeing. So we start at the retina, the photosensitive retina at the back of our eye. That's where light is registered before light signals are bundled together at the back of the retina through all these pathways or axons. They come together to form the optic nerve, and those patterns of light signals go up to our brain. And because you need to get the light signals to go up to the brain through the optic nerve, there's a space in front of where the optic nerve is formed that's called the blind spot. You can't see on the blind spot. So no light is registered the positions of the blind spot. And you might say, big deal. But unfortunately, the blind spot, if you look at the retina, is as big as the fovea. And the fovea is that part of the retina that has most of our visual acuity. The reason we make saccadic eye movements several times a second is to point our fovea to the things we want to see. Everything outside the foveal range is sort of fuzzy. You can't use it for effective recognition or seeing. So, given you have a huge blind spot, you couldn't look at or reach for any object that happens to its light hits the blind spot because there's no registration there. So that could lead to disaster because it's as big as the whole fovea. So you're led to realize, though, well, we're not aware of those missing signals over the blind spot. And that's because higher up in our brain, we complete the visual representation over the blind spot so that we can look for and reach to things all through the visual field. And the question is, with not going through every detail, how is this incomplete image completed? And here you got to do a lot of vision. And I'm the guy who introduced the main models with the help of gifted students, because you need to do what's called boundary completion and surface filling in. And we could talk about that till the cows come home. Boundaries and surfaces are the foundational mechanisms of 3D vision. Everything in our world that we see is seen as a boundary or surface. And it's very
no coincidence that essentially defines what physics is at the same time too, right? This recognition that physical bodies are defined in the same way.
That is a wonderful comment, because boundaries and surfaces as understood in the brain is not defined the way you define a boundary or surface in physics. For example, in physics, if I have a surface, you'll have little normals sticking up in every which way to give you the shape of the surface. That's not how surfaces form. Surfaces are formed by filling in. And why do we fill in? There are multiple reasons. One reason you fill in is to cover the blind spot. Another reason you fill in is that we see the world in variable levels of illumination, from very bright to very dark. And we have to compensate for that variable illumination. It might be 5-6 orders of magnitude. And we discount the illuminant. And that throws away a lot of the image. And then you got to fill in off the remaining part. And I explain all that. It's Wonderful. I love vision. And I call that process of going from an incomplete image to a complete one hierarchical resolution of uncertainty. Remember, I was saying there are uncertainty principles in brain as well as in physics. And I say it's hierarchical because it takes multiple stages to do. And then you have to ask a simple question any child could ask if they got this far. Well, how does the brain know at what stage the cortical representation is complete enough to use that stage for looking or reaching? If you used an earlier stage with incomplete representations, you might not survive over the next 5 minutes. And the answer that I've been led to, conceptually and in the service of explaining very challenging data, is a resonance form with a completed surface representation and the next processing stage. And it's that resonance that lights up the completed surface representation and renders it consciously visible.
What is the process? What is the process by which a completed surface representation, so to speak, is decided upon as being sufficient?
Well, that's what I just said. So first you have to understand how you complete boundaries and surfaces. It turns out that our brains are designed so that it gets as complete as it gets by pre-stride area V4. And so the goal is to use that representation for looking and reaching. And so V4 and the next processing stage, the posterior parietal cortex, V4 sends its representation of PPC. PPC sends down excitatory signals. They form what I call a surface shroud resonance that lights up the completed surface representation. And PPC top down is spatial attention, but bottom up to higher levels of the brain, it controls looking and reaching. So it's the interface between perception and action. Okay.
I guess the question that I'm asking is not necessarily just inside the human brain, but it seems like the idea of sufficient complexity for a surface must come before the human brain, right? It must because there's this innate aspect of it, which is that there is something that is complete enough, that is primary, which the brain is then structured in order to be able to set that condition to say, here we go, that's good enough. And that has to predate the human brain.
It does. Same thing would happen in monkeys and lots of other animals that see. It has to be the most complete representation you've got in your head. And that's the one you light up. And then you might say, well, what about all the earlier stuff, that garbage? Remember, I talked about the art matching rule. And so first, this is conscious seeing. But I also talked about art in terms of recognition, where a feature category resonance, which we talked about, but I didn't have the ability to finish the sentence because we moved on, that supports conscious recognition. And seeing and recognition, not the same thing. But these two streams, V4 can be an interface in going to inferior temporal cortex to categorize. And so you can have a IT, infratemporal cortical, V4 resonance for conscious recognition. At the same time, you can have a V4 parietal cortical representation for conscious seeing. And when they're both active and synchronized, that's when you consciously know about something that you consciously see.
And is this borne out Is that borne out in examples where you've mentioned that you studied people that had brain disorders? And I know that there's brain disorders where someone can look at something and not recognize what it is, like a face.
Yes. Yes. Well, first, keep in mind now, I want to say another thing before we get to that. Keep that right in though. Posterior parietal cortex is going to the where stream. Space and action. As I said, parietal cortex can help direct looking and reaching. And that's the dorsal cortical stream. Whereas going to infratemporal cortex, and in speech and audition, it wouldn't be infratemporal cortex, it would be a different temporal cortex. That's in the ventral or what cortical stream. So you have this huge resonance between the dorsal and ventral cortical streams. And moreover, by the art matching rule, once that resonance starts, remember the art matching rule with its modulatory on center and inhibitory off surround, it's going to go racing through all the cortical layers to select the patterns that are consistent with the feature category and surface shroud resonances. So you're paying attention to consistent data, and it goes all the way up to prefrontal cortex. So at that moment, your entire brain is resonating on the stuff you're paying attention to and interested in. Baby, you can't do that with a feed-forward adaptive filter.
Mm-hmm.
Okay? We're in a different universe. Okay, did I say that well enough? And so let me now say, so I don't forget. So as of this point in my life, let me see, do I have these things? So I don't want to have to do it from memory. There are 6 resonances that I've classified so far. And by classified, this is the end of the story, not the beginning. The beginning of the story is my gift mainly is seeing the intuitive meaning of data. I eat data, breakfast, lunch, and dinner. My brain is filled with facts. And then somehow I begin to understand the intuitive meaning of the data. And then gradually through an affective and visual process, I find words to describe what I'm feeling and seeing, and ultimately equations and systems. So I mentioned surface shroud resonances support conscious seeing of visual qualia. It's called a shroud. It's not my name. It's the name given by Christopher Tyler, who was really interested in how spatial attention can spread to cover a surface that you're paying attention to. So in other words, you might have heard of a focus of spatial attention. You know, it just can send a little beam of attention. But that, through feedback, then spreads into a shroud so that you're not looking at this pixel and that pixel. You're looking at the whole thing, but I can volitionally control the scale of the beam so I can look at parts too.
Well, it's like sometimes when you look at someone, you can look at their eyes or you can look at their nose, or sometimes you can zoom out and you can see the entire face. But during a conversation, when you're looking at someone, there's this practice of going back and forth. And I always have to get out of that space where I'm like very closely examining people's faces as I'm talking to them. And I have to be like, no, take a step back, look at the face.
This is the hardest part, by the way, about mixing audio recorded music, as well as because you want to pay attention to each one of the instruments very carefully if you're the audio engineer. But at the end of the day, the end user just wants to hear the whole piece of music. And so maybe you spent 3 hours miking this saxophone so that you would hear all of the wind sounds and everything. But ultimately, it doesn't matter because the person wants to just see that fully almost out of focus picture all at once.
Oh, this
very tricky thing to pull off.
Then you have to think about musical geniuses like Mozart and Beethoven. Beethoven being able to write out the Ninth Symphony when he was already going deaf. I mean, it's pretty amazing. So surface shroud resonances for the conscious seeing. I mentioned feature category resonances support conscious recognition of visual objects and scenes. Then there are stream shroud resonances that do the same thing for hearing. They support conscious hearing of auditory qualia. And then coming to music, there are the spectral pitch and timbre resonances that support conscious recognition of the sources in auditory streams, as in the cocktail party problem, which my work offers a solution to. At a higher level, there are the item list resonances that support conscious recognition of speech and language, because items are stored in cognitive working memories and patterns. And when they're categorized, I call them lists because, they can be categorizing a syllable, a word, a phrase, a lyric, and using the same mechanism for all of it. So I like using the word list because there's a shared unifying mechanism. And the mechanism is there. Why is it unified? So that you can quickly learn these complicated patterns in your working memory without catastrophic forgetting. And I derive the models for doing it from two simple hypotheses like that. And then the cognitive emotional resonances support conscious feelings and recognition of their sources and help to direct us to realize valued goals. Now, that's an illustration of all conscious states are resonant states. But it's not true that all resonant states are conscious states. And I can give you examples of resonant states that aren't conscious states. For example, there are entorhinal hippocampal resonances that help to support the dynamics of entorhinal grid cells and hippocampal place cells in us when we do spatial navigation. And there are parietal prefrontal resonances that help to regulate the opening and shutting of basal ganglia gates for enabling cognitive, emotional, and action to occur. And you might say, well, why aren't they conscious? Why don't we have names for them? But we have names for things like seeing, hearing, feeling, the things that support qualia. And that is the answer. All of the conscious states that I mentioned before, those first six, support either external, resonate either with external sensory cues like visual, auditory, whatever cues, or internal homeostatic cues like fear or pain, etc. But the ones we don't have names for that never become conscious, they're not linked to any qualia of any kind. So,
do you think that's the case also for people who are deep meditators that are really aware of their bodies and are able to reflect more closely on internal states? Or you think that that's a universal block from recognition?
Well, that, discussing the how and the wherefore of like going into a Zen state is a complicated topic in its own right. And I'm not an expert on Zen, but I have meditated a lot in my life, just my own little personal meditation. But to me, it just seems that helps you to clear yourself from focal attention. You're not focusing on little this or even a face, or you're just resonating on your feelings. And one of the feelings that I think goes into trying to get access to in meditation is what is called in the reinforcement learning literature relief. You get this feeling of well-being. I wish I could. Oh, yes, the relaxation response, right. What was his name? Was it Bender? Something like that. I write about the relaxation response in my book. But the relaxation response is another word for what many people think of when they're meditating or in Zen. And I discuss how that can happen. And it's sort of the opposite of focal attention. It's just, opening yourself to the irradiation of your whole system with this feeling of well-being, whose causal link, I believe, is in relief. And now, relief is a very interesting property of our emotional system because you can be afraid, learn to be afraid of some situations. Let's say, if you're being a little sadistic in a Skinner box, you can put pigeons and you electrify the floor. And the pigeons are feeling terrible pain and they're trying to keep their feet off the floor as much as they can. And they're stumbling and tumbling and running all around until finally the pigeon luckily hits a red buzzer. And when you hit the red button, the shock turns off. They feel a huge wave of relief. And they use that positive motivation and affect to learn the link between seeing the button, running to it to shut it off, so that they can then have efficient escape and avoidance whenever they're in a fearful situation. And that's why, for example, there's people with post-traumatic stress disorder. They can be counter-conditioned to think positive thoughts when they're forced to think about what caused them negative thoughts. In other words, they were in a negative feedback loop with terrible sights and sounds and fear and, all these awful negative feelings. And a good therapist will gradually try to find salient positive situations and thoughts so that forming a positive feedback loop with them can competitively inhibit the negative affective source. And then, with time, they can get better and better at thinking the positive thing to inhibit the negative. So one of the main things I discovered very early on, and which was really important for my work, was how and why we have competition in our brains and how you design competitive interactions to choose the most salient category or feeling to use in coping with a given situation. And so, I derived my competitive networks from another thought experiment, which is called the noise saturation dilemma. And if you want me to say in words what that is, I'm happy to, but I don't want to go too far afield. Whatever you want.
Well, I feel like I still don't understand why there is a large population of people arguing that the hard problem of consciousness is persistent. Why are people not taking this idea seriously? Or maybe that's not the right way of putting it. Maybe why are not more people taking it seriously?
Okay, well, first of all, I'll get back to a direct reason, but remember Isaac Newton we know is one of the greatest scientists of all time. And he published the Principia when he was in England. No one in England gave a damn about his work. It took Voltaire to proselytize his work on the continent before Newton's work started to break through. Unfortunately, by the end of his life, he became the Lucasian professor of natural philosophy. So there are quite a few people who have said and written wonderful things about my work and used it. And you just have to read the reviews, not only on the book jacket of my magnum opus. Some of those people are among the most famous psychologists, neuroscientists, and technologists in the world. But look at the reviews, the 130 or some odd reviews that came out post-publication on Amazon. All but one review is 5-star. And two of those reviews by different people call me the Einstein of the mind. I think it's because if you have cliques or even cults who, for whatever reason, it's not in their self-interest to broaden the discussion, they will try to maintain their power and money and fame as long as they can. And remember what I said back in the old days. It was my impression when I visited UCST that Dave Rummelhart students only knew backprop. Whereas in our department, we try to teach them everything. That is, I guess, a difference.
So if I can steelman what I think is the perspective on the hard problem is that the way that art, the way that I understand it is that it's already dealing with the systems that are in place, right? So you can teach a pigeon to react to an electrified Skinner box, to recognize this button, and then to do something. And so it's already a really complex system. And when people talk about the difficulty of the hard problem of consciousness, I think that it tries to zoom out somewhat and try to understand why the experience emerges in the first place. Because the idea, as far as I understand it, is people are like, look, you can get the whir of information and make some kind of decision on the basis of the whir without any of the higher level emotional, sensory, perspective reactions that are defined as qualia.
If you take to heart, I'm not saying anything I say should be understood or agreed with the first time I say it. But like I've had many times in my life experience, I'm giving a colloquium, I see a familiar face, I know I've spoken about that topic when he was there, and I said, why'd you come again? He said, well, each time I hear you talk, even on the same subject, I learn something more. So remember what I said about the retina. That it gives an explanation of why we have surface shroud resonances. It's to try to select the complete surface representations for looking and reaching. It's not abstract. You would not know where to look. You would not know how to pick up your fork and eat without that. So don't tell me abstract, obscure. No, foundational, basic. You have used it every minute of our interaction. It's a cop-out.
I mean, it makes perfect sense to me. That's what's so mystifying about this whole debate to me is that, are you telling me that somebody like Joscha Bach is just entrenched in his cult because it's necessary for him to produce a career now that he's staked his claim that the hard problem of consciousness is unsolvable? Is that the only reason? Like, does he not understand?
I have a really hard time believing that that's the reason, because his purported goal is to build these systems that are capable of intelligence and consciousness.
Wait a second. I've got to tell you that I had a Zoom discussion with Yosha, which he invited me to, where I explained all this.
That's what I'm saying.
He invited me because he appreciates my work. But what you're saying is and what do you do when you deal with the living, breathing Einstein of the mind, who has been working like a dog with hundreds of collaborators for over 50 years? What do you do if you cannot contribute something new? That's what I mean when I say that's the moment that tests character.
Well, there's a lot you can do.
But let me just say, Voltaire decided the best thing he could do is try to spread Newton's discoveries to the continent.
And put them into words that people understood, right? I think this is highly underrated in terms of the production of scientific paradigms. It's being able to take your ideas, put them into a phrase that a normal person can walk around with and talk to other people about.
I agree. And that's why I spent years writing my magnum opus. And remember, we're talking about our little gray cells. It's arguably the most complex system we know about in the universe. So it is going to be a challenge. But I have friends, a rabbi, a pastor, a visual artist, a gallery owner, a social worker, a lawyer, etc., who picked up the book and read parts of it with pleasure and understanding. They know no science. Okay?
I think that we have to establish at the foundational ground that we are of the school of thought that agrees with your perspective, right? Like, I have never understood why there is a hard problem of consciousness, because it seems apparent that you couldn't function without these modules in place, because otherwise you'd have, like, will is a huge part of this, right? Because the things that you see and that you encounter are not value neutral. They come down to the fact that you want something and you have to interact with your environment in such a way that it allows goal-oriented behavior. And so you can't have just a soup of information, because you have to have a hierarchical system of rewards and some kind of recognition that if you take this action, it will then feed back in time onto the person that you were, that had the goal in the first place to bring you closer to who it is that you want to be.
Like, I completely agree.
Let me respond. But I don't quite agree with you, because there is a problem. And in your comment about, it's so obvious and so on and so forth, number one, you never use the word resonance, so you haven't explained anything about it. But number two, you used another word very lightly that I've spent decades studying. You use the word will, which is volition, which is all about how the basal ganglia interact with perceptual, cognitive, emotional, and motor systems. And if those gates don't open and shut in the right way, in the right context, you can become a Parkinson patient who can absolutely lose your mind. First, you can't move right, but ultimately you'll feel crazy and you'll think crazy. And I have a whole chapter about the basal ganglia in my book, not as an isolated thing, because it's meaningless in isolation. It's a system-level understanding of how this subcortical structure interacts with just everything that makes us human. And it took me decades to even know what questions to ask about it. So, it's hard. I mean, if I have always been a glass half full person, and whenever someone taught me something that I didn't know, I was grateful. I would cite them. I would promote them so that other people could enjoy that insight. I'm not threatened by that discovery. I'm relieved by it, because if it's in the field I work in, hey, that's something I don't have to do. They did it. Great. Isn't that wonderful?
Mm-hmm.
What happens when you encounter an idea that has some good pieces to it, but overall you think that it's flawed? How do you work forward on that, and how do you deal with the citation and so forth?
Well, I do my best to not only cite the proximal people, but also historically. If you look at my book, you see Helmholtz, Maxwell, and Mach, and Pavlov, and others. In fact, my book had almost over 1,000 figures in the first version. It was 800. It was 1,000 pages long, and Oxford Press said, "Hey, Steve, that's more than we want to handle." So I had to cut out all their pictures. I had their photographs. I was honoring and celebrating them as just a subset of the people on whose shoulders I stood. I had pictures of Pavlov and Skinner and Thorndike and in all these streams of activity. And I go through, I do still have a review of, I forget, linear without learning, linear with learning, at the beginning, is it chapter 3? I do that to give this history, but without as much elaboration as I first wanted, because I think it's very important for students to know that the struggle to approach insight is a cultural community struggle. Even Newton built on Galileo and whatever, we're all building on the shoulders of giants. And that's one reason for years I sort of try to hide in the bushes. I didn't want to have people call attention to me, because I saw so many examples where, someone becomes famous for this or that, and it totally destroys their ability to do good work. They become personalities.
Mm-hmm.
They're going on, the Tonight Show or something. And it's then when I got to a certain age, now I'm 83, I figured in the last few years, okay, you want to make me famous? I'm ready. Do it before I'm gone, So
Let me ask you this. I would love to be one of your Voltaires, but can you put it into a sentence if somebody was to ask you, okay, this guy has solved the hard problem of consciousness. What is it? Could you do that? Can it be fit into a sentence?
What is my solution?
In a sentence.
Yeah, well,
can you do it?
Well, I would say we take for granted we can do things. Let's first start with vision. We take for granted we can do things like looking and reaching. But how does our brain know when it has a good enough visual representation to use for looking and reaching? And that's what this man has shown, among other things. It knows how to select the stage that did it so it can be used for looking and reaching, and the brain's organized to use that information to look and reach. And that
so the hard problem of consciousness
explains the why, because we couldn't do the looking and reaching without the conscious state that lets us see what we're looking and reaching at. And, you know,
so the selection, the attentive selection is what solves the problem.
But
The need for attentive selection, I would say.
The attentive selection and resonance that makes the visual representation visible to do the looking and reaching. And now you might say to me, let's turn it around. And I've thought about this a lot. Let's say Google or God knows who in the future takes everything I've discovered and everyone who's done other excellent, useful work, and they build it into an autonomous, adaptive agent that's capable of machine consciousness in the sense that it embodies all the resonant mechanisms that I've talked about. And let's say these dynamics are isomorphic with the dynamics of the mathematical models that are used to parametrically explain data about how we look, reach, talk, feel, which is why we believe they're relevant. You still couldn't say why water is wet. You couldn't say why red light looks red. An equation cannot give you qualia. An equation can just give you a mathematical description of all the properties of the qualia that you might use in life and experiment.
That's right.
That's the same thing as in theoretical physics.
That's right.
You don't have to go on an autonomous vehicle around the moon and have it come back to Earth. You don't have to personally do that to know how it worked and to have faith in it. Remember that famous incident, I'm not sure if I could say it right, when a space capsule came back and the question was, what was the bump there? They had predicted there would be a bump when it landed. And the famous reply was, yes, the bump was there. They had that trajectory down pat using celestial mechanics, which Jürgen Moser was a great expert on.
So it sounds like to me what you're saying is that mathematics is only capable of describing what's going on. It's not capable of actually explaining the qualitative aspects of it. And so seeking a mathematical explanation for the hard problem is the wrong frame.
That's too broad. What math can't do is give you the qualia.
Well, math can't explain anything by itself without some sort of language accompanying it to tell you what the variables are, to tell you what processes are at play. It's not a complete language.
But all that's missing is the qualia. Okay. So remember, when we're reading about and physicists are doing theoretical or experimental physics, they are using their conscious mind to guide their looking, their reaching, their building, their everything. We have to keep in mind that this is sort of beyond theoretical physics, but it makes theoretical physics possible. And that's why at the end of my book, I talked about, we've been adapting to the physical worlds all of our forebears have lived in for millennia to try to learn how to succeed in them. Darwinian selection is just one way of thinking about that. And that's why I find it so interesting that principles of resonance, uncertainty, and complementarity that occur in the description of physical laws also occur in the description of mental laws. In fact, I didn't say today, boundaries and surfaces are computationally complementary, strictly complementary. Knowing and acting are computationally complementary, but on a totally different scale.
Well, that's an interesting point, because they are complementary, except for the fact that complementarity can be broken sometimes, right? Because somebody can know something, but act in contradiction to what they know for an entirely different set of reasons and influences that are not the same as knowing.
Complementarity is a statement about the structure of our brains. Your comment is how we use our brains to do things. Complementarity is still there. Okay, the fact is that I've shown, and I can give you examples of it. Maybe I can give you a picture today.
I feel like when people are really, in the best case scenario, when they're talking about the hard problem of consciousness, what it seems like they're talking about is that second order variation that lives above the complementarity. Because the complementarity, if I would put it into the language that people use for the hard problem, is about the neural correlates. So there is this resonance.
The complementarity is about how everything works. For example, you can see that?
Mm-hmm. So a set of lines that are basically offset from each other.
Yeah, and now if you see it under the right conditions, you can recognize there's some vertical boundary going between the lines.
Mm-hmm.
Do it at home if this isn't good conditions. But that boundary is invisible. You don't see it. You consciously know it's there. It isn't darker or brighter or a different color or a different depth. It's conscious knowing of an invisible thing.
To put it into the language that I've heard people use, it would be that it is information, right? So you have on the left...
No. Information is vacuous. It's a vacuous term. Look, information theory was discovered at MIT for very specific purposes to define communication channels and their capacity. It has nothing to do with the brain. Nothing. It's serial and binary. The brain is parallel and analog. It doesn't self-organize in its original form. The brain is all about self-organization. So the point is, let me make my point again. All boundaries are invisible. This is a counterexample. So then how the hell do you see? Well, you see because boundaries support the filling in of surface brightness, and we see surfaces, not boundaries. And let me give you an example of that. That's why I love vision. I don't need a super collider. So look at that. See?
Mm-hmm. So now this is a radial pattern of lines that end in such
disk, if you look at the inner disk, it's brighter than the exterior. Okay. Mm-hmm. Of course, it's not brighter. I just drew those lines.
So there's like the imprint of a circle in the center, but you can't actually see.
Wrong word. You need the right words.
I'm just trying to explain to people at home so that if they're listening, they can understand.
But that's a bad word. Let me give you the good word. I drew what's going on in our brain. At the end of every black line, there's a little local enhanced brightness. It's called a brightness button. And why don't you see that? Because without another boundary there, you don't see it, because what's happening in our brain is due to those line ends, we are constructing an emergent circle.
Mm-hmm.
And you might say, well, why don't I see that boundary? Well, you don't see the boundary because all boundaries are invisible. but you see the surface inside because those brightness buttons now fill in and spread all through the interior. And they're brighter than the background. And so the whole surface looks uniformly bright. So I've given you an example of how, although boundaries are invisible, boundaries interact with surface processes to create visible surfaces. Even in the case where there was no physical brightness difference. And that's one reason why, for many years I was fascinated by studying visual illusions, because when things don't look quite right, they call your attention to, hey, what the heck is going on? And that's one reason why a lot of the greatest visual scientists studied visual illusions, including the great Gaetano Canizza, who lived in Italy and was alive while I was working.
And so at what level of complexity do you start to be able to see these visual illusions? Because one of the things that I hear people talking about a lot is that there is an implicit understanding that something like a bacterium is not conscious. And I've never really been satisfied with that.
A bacterium doesn't even have a visual system or even a brain. So yes, but in chapter 17 of my book, again, I talk about examples that I like very much. So in terms of bacteria, you can have the bacteria that go into, these bacteria, no, these are, I think they are, that go into slime molds, whatever the units that go into slime molds. If there's a lot of food, they spread out and they just do their own.
Are you thinking about, I think that it's Dictyostelium discoideum, the one that goes from the general... I love that.
It's actually a fungus, I believe. Just for
we're going very primitive. That's what I want to point out. And what's fascinating about it is that, as you know, if the food supply gets sparse, it aggregates to form a fruiting body. And by that change of scale, it's now big enough for water currents to carry it way downstream, at which it disaggregates, etc. Why am I telling you this? Because if you study how it works, it is an on-center, off-surround network. There is, actinogen? I forget what the chemicals are. We know the biochemicals. Locally acting positive attractors and globally acting inhibitory repellers. And it is the collective action of those on-center, off-surround little networks around each unit that regulate the coming together and going apart. So it is, in other words, the idea of on-center, off-surround is way before a brain. It's very early in evolution.
But is it a mind?
Well, and okay, so that's exactly where I want to go.
No, I don't think so.
And so I think that when people talk about the hard problem of consciousness, what they're really trying to get at is they're like, how do you go from this, you said it, off-center, on-surround system to the mind, which appears to be something that is far more complex and is resistant to the simplification down to just modules.
So if you look through my book, I give an evolutionary. I can't replay evolution. We don't even know all the aspects of how it worked. But I can do a conceptual evolution of how we started with incredibly primitive little networks and how that step by step built up into a much more advanced brain. And if you follow, I forget what chapter it's in that I start doing this. I do a stepwise analysis showing, I include crayfish swimmerette, songbird, uh, um, pattern generators. You can go through multiple species in this way. And I find it very helpful to illustrate the universality of the dynamical laws that have gone into our intellect, in our mental heritage. But as to the hard problem, first, don't get fixated on it. I think I've given a really good description of what's going on there. There's so much more, but for example, in my description of a possible way of understanding the hard problem, first you have to know a lot about vision, how we see, and how we use seeing to look and reach. Likewise, if you want to understand audition, you have to know how we hear and use that to learn to speak and, think, etc., and communicate. So,
can you give us an overview of the evolutionary model that you have for this? Because I think that it would go a long way towards me being able to present these ideas. Because when we talked to Yosha, it was very frustrating because we talked about this idea of resonance and the resonance systems and the feedback and the multiple levels, and he was unsatisfied.
What did he say about that?
He said that it was too vague. He said it was too vague. He's like, that's too vague for
bullshit. Me. I'm sorry, Yosha, bullshit. You should be embarrassed. Because all you have to do is pick up my papers where I prove theorems about it. And there's nothing.
Well, I didn't have the mathematics on hand. So like in his defense.
No, but he knows the work. I think he interviewed me, I don't know, somewhere between 2 and 5 years ago. I can't keep it straight.
That's what's so perplexing to me is how he can know the work and still remain unsatisfied with it. And I don't have a sense of what he's unsatisfied about.
I can't speak for other people. I mean, I like him very much. I'm sure he has his personal reasons. In order to advance theoretically what's already been discovered, you'd have to work very hard. If you want to proselytize it and teach it, you don't have to work quite so hard. But if you want to toot your own horn, you don't have to work at all. So I can't speak for it. I like him. I think he's a solid guy. I'm sorry that he doesn't get it. But, to me, one reason I keep working is because of the beauty of the answers. I mean, things I never dreamed I could talk about, let alone think about, problems I never realized needed to be solved. When I was a boy, I've now, with my colleagues, helped to make really clarifying contributions and explanations of it and simulated them. And a lot of them have gone into applications, really big applications. So for me, I just feel I've been given a priceless gift, and I would never, ever try not to honor it. And while I have the strength to keep making discoveries, I will. I have a paper in press now talking, you mentioned ChatGPT. If you want to talk about that, I'm happy to. But what it's about is how children interact with teachers, like parents or other teachers, in order to learn language meanings. Both, that language utterances stand for objects seen in the world or feelings that we have about the world, but to write that paper, I had to know a lot about how we see objects consciously and recognize them and how feelings interact with our thoughts. And you can't talk about meaning in a detailed, explanatory, neurally relevant way without those insights. For example, just in terms of recognizing mommy, you have to solve the invariant pattern recognition problem to recognize mommy from any viewpoint. But then to know where mommy is looking or reaching, you have to be able to also recognize the view of mommy's face and where her eyes are looking, and how by knowing where she's looking, you can figure out where she's reaching. Well, that's a solution of the joint attention problem. I'm the only person with my student Tony Vladosic, who I believe has provided even a partial explanation of how we do joint attention. And it has to do with shrouds. Who knew? Who knew?
I mean, we've done almost 3 hours today, and I would really love to talk to you about ChatGPT. Do you think that maybe later in the year you would be willing to come back and talk to us about that? Because I think it warrants.
You have 5 more minutes?
Yeah, we have 5 minutes. I know that our conversation with Yosha went for about 4 hours, and people were very upset that it was so long. So we're trying to keep them to 3 hours-ish.
No, but you don't have to use it. Is this live? I don't know. Is this live?
We don't edit unless we have to. We'll edit out the bathroom breaks.
Okay, well, you can just cut it at the end. So ChatGPT, I'm not an expert. Of what I know about it, it's a huge lookup table. So OpenAI just collected facts from the whole virtual universe, which are there in the millions, the start of which are just millions of pictures of cats. So they have this immense lookup table and a probabilistic algorithm. What does the algorithm do? Give me a list of 4 or 5 words. The probabilistic algorithm tries to predict what the next 4 or 5 words will be. And it keeps going this way. The problem is there's no concept of meaning. There's no concept of values. There's no concept of goals. There's no intelligence whatsoever. Mm-hmm. It's just a predictive lookup table. When there was learning that went into whatever learning went into the database, they used deep learning. I've said all I need to say about deep learning. That's the end of my talk there. You'll never get meaning. It will hallucinate. You must know the famous story of the lawyer who recently produced a case based on cases that he got from ChatGPT that were all confabulated. None of them ever occurred, but they sounded good. And then when ChatGPT was queried how much confidence you have in these cases, they said pretty much. Does anything else?
It's very disturbing to be lied to by an AI. It's very, very, very weird feeling.
What I want to say is, if you joined ChatGPT with everything I've discovered about how speech and language work and how we do use values to guide the selection of the sentences and thoughts we're going to have in a given context, that could be a huge revolution and a little scary.
Yeah, I was going to say, or a nightmare, a huge revolutionary
that could be
nightmare.
Very scary. And, like this guy who released it to the world apologized later. Oh my God, we didn't do this constraint and that restraint. What were you thinking of then, buddy? It's your fault if people want to sue ChatGPT for damages, you are fully liable, because just as I said with using untrustworthy, unreliable deep learning predictions where they are not explainable, ChatGPT is not explainable, and you are liable for every cent you're worth. So it was a colossal act of hubris and very unfair to people who just believe what they're told, that this thing wasn't monitored more appropriately, including with congressional oversight of how it could be released, for what purposes, and so on, to what audiences. They're just out to make a buck. Very sad.
I mean, I think that there's a lot left that we haven't been able to dive into because the extent of your work is so massive. You've really looked into all of the details of how these processes in the mind work and how they come together to create the experience of living, and it's not possible to cover it in 3 hours. And so I think that we should just put a pin in it and then have you back. One of my favorite things is being able to have repeated conversations with people that spend so much time thinking about deep questions, because it's just not possible to gather everything from you. And even though you've written this book and you have such a wealth of publications, there's still something ineffable about being able to sit you down and hear you react to these questions in real time.
Well, I have enjoyed talking to you very, very much. I don't know how you advertise your stuff, but I wouldn't mind if you made the header "Talking to the Einstein of the Mind," because I'm not the person who called me that.
Well, Ogi Ogus actually told us that you were the greatest scientist that had ever lived, and so this is what piqued our interest in the first place. So,
well,
no lack of accolades.
I'm up there with people who I revere, and the incredible fact, which I couldn't have predicted, I have been making discoveries at a feverish rate for 66 years. And I haven't stopped. And the lesson is I've always honored the fundamentals, the foundational principles. Taking shortcuts, you'll hit a brick wall. I've never hit a brick wall. And that should be the lesson of my life. Being authentic and honoring the data, the sources. And I have sometimes worked for over 20 years to be able to find the words, the vision, the images, the feelings, the words to explain something which seemed so mysterious to me at the beginning. And I was always so overjoyed by the fact that the explanations basically have simple reasons, like why do we consciously see? To look and reach. But to make that into a scientific theory, that's when, something hits the fan or whatever. And another thing that I think is really useful is what I call the gift that keeps on giving. Because often I've made a discovery and then I work out some of the details, and it opens my whole world up to things I never even dreamed of before. It was a gift that kept on giving, and that launches me into another area I never thought I'd talk about, think about. And it's still going on. I don't know how much longer I can keep the ball in the air, but look, if I go today, I can only say, thank you, Lord. It's been a great ride. And I hope that more and more people benefit from the work and appreciate the lesson of my life, which is to be true to your ideals and to the facts you're trying to explain, and not to sell out for a short-term gain.
Right on.
It's beautiful. It's a good idea to end on.
Well, thank you. I've enjoyed this. I hope I haven't been too egoistic and egotistic, but you are, after all, talking about my work. So I got to go with the flow there, don't I? So wonderful. Thanks, guys. Hey, you're a couple, right? Are you married?
Mm-hmm. We've
Nice.
been together for 10 years now.
You've got a good resonance between you. Interpersonal resonance and synchronization of minds. Big topic.
We'll talk about it more next time. Thank you.
My pleasure. Bye-bye.